The basic underlying difference between classical mechanics and quantum mechanics lies with uh, what is called as Heisenberg uncertainty principle. In classical mechanics, what we do is, so to find out the future state of the system, what we do is we measure the initial quantities such as position, momentum, etc. And we have set of connecting equations. So for example, if you have an object which is moving under constant acceleration, if you know the position, initial velocity, the initial parameters accurately, then always you can find out the future state of the system to the same accuracy. So in the sense, we have set of connecting relations which you have studied at your PU level. Like, say for example, you want to find out the final velocity of the particle. Then, if you know the initial velocity, then you can find out the final velocity of the particle by using a relation v is equal to u plus at. Similarly, you can find out the distance traveled by using s is equal to ut plus half at square, etc. So the final system of the particle is exact there. But in quantum mechanics, it is impossible to find out certain quantities which intrinsically depend on each other. Such quantities are called as canonically conjugate variables. So, for example, position and momentum in the same direction. Say position of the position coordinate x, position of the particle in x coordinate direction, and its momentum component. So they do not commute with each other. So in the sense, so they cannot be measured simultaneously. Always there will be some error involved in their measurement. So since there is error involved in the measurement, so it is you cannot find out the system accurately uh, and simultaneously. Hence, future of state of the system is only the probability. But the thing is, uh, this probability, whatever you measure, so that coincides with classical results for larger dimensions. And this is what is called as Unfest theorem. So therefore, in a way, classical mechanics appears as an approximation of quantum mechanics. Now we'll apply the classical theory, the quantum mechanical theory, quantum mechanical postulates so far what we have studied, so as to a simple problem. So that is particle in one-dimensional box. See, the description of the problem is as follows. So you have an infinite well. That means the well height is infinity. So it is of finite width. So the width of the box is about 0 to a. That is a meters, but the height is infinity. So this box has rigid walls. So that means, or if you have a particle inside the box, so that particle is totally trapped inside it. So because it cannot jump out of the wall because the wall height is infinity, and also it cannot penetrate through because the walls are so rigid. Potential for such a problem so is given by these equations. So v of x is equal to 0. That means the particle inside the box. So that is from 0 to a. So if x lies x is less than a or greater than 0, that means within this dimension of the box, so the particle is free. So that means no force is acting on it. So that is why no potential. Potential is 0. Whereas outside the box, the potential is infinity. So on this region or in this region, so the potential is infinity. So for this kind of problem, so we'll apply Schrodinger equation and we'll find out the eigen values and eigen energy values and eigen functions. See, this is the Schrodinger equation inside the well. Inside the well, you have only, the particle has only kinetic energy. So that is minus h cross square by 2m. So it is one-dimensional problem, d2 by dx2 psi of x is equal to e psi of x. And taking this k square is equal to some 2me by h cross square, or k is equal to square root of 2me by h cross. So then you get this equation modifies to this form, d2 psi by dx2 plus k square psi is equal to 0. You know, this is a second order linear homogeneous differential equation. So we know the solution for this. Accelerated equation will be d square plus k square is equal to 0. So therefore d is equal to plus or minus ik. So you get oscillatory wave functions. So psi is equal to a sin kx plus b cos kx. So this a and b are constants, arbitrary constants. So one can find out the values of this arbitrary constant by using the boundary conditions. So since x as at x is equal to 0 at the first boundary, the wave function is 0 because particle is present only inside the box, so it cannot present at the wall. So at x is equal to 0 and at x is equal to a, so psi of x should be 0. So this is psi of 0, psi of a will be equal to 0. That is at x is equal to 0 and at x is equal to a, so the wave function goes to 0. So if we apply the first boundary condition, so that is psi of x is equal to 0 at x is equal to 0, we get sin k is equal to sin b is equal to 0. So because a sin kx plus b cos kx, so that is a sin 0 plus b cos 0 is equal to 0. So anyway, that sin 0 is 0, so the first term becomes 0. Whereas b cos 0, so cos 0 will be equal to 1, so you get b is equal to 0. So that is the first boundary condition. If you impose the second boundary condition, so that is sin k is equal to 0, then you get k is equal to 0, so plus or minus pi, etc. So that means for all integral multiples of pi, sin n pi is in fact 0, so you get ka is equal to these things. So from this we get kn is equal to some n pi divided by a. So you will see that this k depends on n, because pi and a are fixed, so it depends on n value. So n, even though mathematically n is equal to 0 is allowed, so we will not take n is equal to 0. So from physical consideration we could take minimum value of n is equal to 1, because if you put n is equal to 0, so then even this sin k also becomes 0, so then the wave function will be 0 all through. So we don't want that. So we know that the particle is there, so therefore there should be a wave function corresponding to that. So therefore we'll start with n is equal to 1. And the corresponding energy is given by this formula, and because already we have defined here, so we know what is k. So k is equal to square root of 2me divided by h cross. So if you substitute the value for k, then you get this En is equal to h cross square pi square divided by 8ma square into n square. So that also depends on n, because all these are constants. Therefore, unlike classical particle can have continuous values of energy. So you can change the energy continuously. So that is the another important difference between classical mechanics and quantum mechanics here. So a classical particle can take any value of energy, so there is no restriction on the energy. But a quantum particle cannot take continuous values of energy. Energy are discrete for a quantum mechanical particle. So for still in this equation, so you can notice that this a is unknown. So the constant a can be determined by using the normalization condition. So normalization condition is 0. So from the boundary, so box dimensions varies from 0 to a. So to integrate this psi star dx. So this psi is equal to psi star. It is not complex wave function, it is real wave function. So therefore psi is equal to psi star. So therefore the product will be mod psi square dx is equal to 1. So if you substitute, you get 0 integration from 0 to a sin n pi by a into x whole square dx is equal to 1. So if you take a square outside, so you get a square into integration from 0 to a sin square n pi x by a into dx is equal to 1. So from this you can evaluate. So this sin square theta is equal to 1 minus cos 2 theta divided by 2. So if you use that relation, then if you substitute here, you get a square into 0 to a half of 1 minus cos 2 theta into dx is equal to 1. And if you integrate this, you get a square. So integration of this will be x. And anyway, this will become 0 for both the upper limits and lower limits. So therefore you get a square a divided by 2 if you apply the upper limit, and for anyway lower limit it is 0. A square a is by 2 is equal to 1, or in other words a is equal to square root of 2 by a. The normalized wave function are given by, so psi n of x is equal to, so you have to substitute the value of a, so that is square root of 2 by a into sin n pi x divided by a. And the plot of the wave functions will be as follows. So if you plot psi 1 of x as for the energy, here also the least value of n will be equal to 1, because otherwise the wave function becomes 0 everywhere and the particle do not exist. But we know that the particle is present there, so that is why the least value of n will be equal to 1. If you plot these wave functions as a function of x, so you get the plots like this. So, and the corresponding probabilities, if you look at, so the probabilities will be maximum. Say, for example, if the particle is in the ground state, so maximum number of the times the probability will be at the center. So that means you find the particle at the center. Similarly, if the particle is in the first excited state, so we call this as first excited state. So you will see that the particle will be at x is equal to something like a by 4 or x is equal to 3a by 4. So you find maximum number of times the particle here, or you find the maximum number of times the particle here. So this the probabilities so are not similar to that of classical mechanics. Classically, if you have some classical particle confined in a box, so it can be anywhere. But here, so it is not so. So the probabilities are not same at all positions. Okay, so this is how one can understand these things, and also you can notice that this is very important factor which is harnessed in nanoscience. So energy is inversely proportional to length square. So that is why, so if you go from macroscopic level to microscopic level, so you will see that the energy level increases. That is why a good conductor at bulk scale becomes, when you go to nanoscale, it becomes either semiconductor or an insulator. So because energy is inversely proportional to A square. So such, this kind of problems finds very important applications in nanotechnology to explain the quantum confinement, etc. So this problem is very much used. Suppose if you cannot solve these problems, see, Schrodinger equation is a second order differential equation. So for all the potentials, it cannot be solved exactly. So when you cannot solve exactly, one can use what is called as approximation method. There are various approximation methods available in literature. So we have something called as perturbation method, variation method, WKB method, orthogonal polynomial method, Hill-determinant method, and so on. So on, and also for multi-particle systems, one can use Hartree-Fock method, etc. So these are used to understand the problems which are physically very important. So if they have a lot of significance, so at least we try to understand them approximately. And the Schrodinger equation which we discussed so far, so is a non-relativistic equation. That means it is valid if the particle velocity is very much smaller compared to the speed of light. Otherwise, so if the particle speed is comparable to speed of light, then we have two different equations. So that depends on the spin of the particle. Spin of the particle also plays very important role. So if the spin of the particle is 0, or if it is a boson, then we use Klein-Gordon equation to find out the eigenfunctions and eigenenergy values. And if the spin is half odd integer multiple, just like fermions, so plus or minus half h cross and so on, so we use what is called as Dirac equation. So we discuss about these things in the forthcoming video lectures. So thank you.